Mm.
Hi, everyone. While we're waiting for our participants to join us, please comment your name and where you're from to the comment section. Hi, everyone. I'm Mina Chemez, and I will be your moderator for this evening. Before we get started, I would like to thank our sponsors, Sage Foundation, and Red Hat for their support on making this event possible. We have the pleasure to start our third day of Bootcamp Week by introducing today's first speaker, Cansu Kavili Örnek, a principal consultant at Red Hat and a leading expert in data science, artificial intelligence, and machine learning. She will guide us through the world of open source, explaining its significance in AI landscape and why it matters now more than ever. Today, Jansu will guide us through the fascinating world of generative AI, showing how it can be used to create text, art, and much more. If you have any questions for Jansu, please write them to the Q&A section rather than the comment section for Jansu to answer after her presentation. So let's welcome Jansu to share her valuable insights with us. Jansu, the virtual floor is yours.
Oh, hi, thank you. So I'll just quickly start sharing my screen and then we actually get from there. So hope you can see in the presentation now. Is everything good? Cool. You can see my screen, right? Is everything okay? All right. So I'll start then. Welcome everyone. My name is Cansu and I'm super excited to be here with you today. I work at Red Hat as an AI consultant, meaning that my team and we help organizations, we help teams to use AI platforms and open source AI tools to solve real world problems, address their business challenges. So I'm a very hands-on technical person, and I hope to get you a little bit of hands-on today as well. So my talk is called as Open Source AI from Users to Makers. So I want to open up with talking about open source first. Like, what is open source? Why I love it so much, and why am I talking about it? And then I want us to discuss about like why open source matters in AI domain, especially today, and talk a little bit about open source ecosystem of today's generative AI's landscape, like what kind of tools and techniques are out there that we can use to make, basic smarter applications. So hope that sounds good to you. So let's get started. But actually, before we start, I have a little question for you, and you can use these like reaction buttons in Zoom, like with thumbs up and thumbs down, or drop some comments in the chat, if possible. So my question to you is, if you had the best chocolate cake recipe, would you keep it secret so only you can bake it, or would you share it freely so anyone can make it their way? So what do you think? Tell me what you think. Hmm? Cool. Oh, share it. Oh, keep it secret. Share it unless I'm running a visa. That's a great answer. Uh, well, you're also sweet, definitely. So now that let's say you share your recipe, and well, some might like bake it as it is, but some might get a little bit maybe creative, then like take your recipes and then add some little strawberries to it because they think it'll taste even better. Or some might make it vegan or add a little bit of a lemon twist. maybe throw some carrot cakes because I do love carrot cakes. And some, maybe they might turn into cupcakes. And that's literally what open source is. Like instead of locking the knowledge away, we share it so that everyone can create it, customize, and innovate in their own way. But unfortunately, I am not in the business of making the best chocolate cake yet. I am bringing you back to the computers and software world. And honestly, I'm not sorry because I love the software world as much as I love a cake. So, what is open source software? It's a software that anyone can see, use, modify, and share. And guess what? It is literally everywhere. Like from the internet that you use to the phone in your pocket. So let's do a little bit of a game again. And again, I'll look at the chats and thumbs up, thumbs down you can use. I'll name some open source technologies, and I want you to let me know if you know about them, if you ever used them. So, okay, I'll start with Git. If you write, no, if you like writing software like me, if you like storing your code, if you are, enjoying versioning your code, you've probably used Git. Git is completely an open source software. You can see how it is built, how it is made, instead of just using it. Linux is the next one. It is the best operating system in the world, and it is 100% open source. So it powers supercomputers, it powers Android phones. Every companies in the world almost they use Linux. Apache, do you know this logo? So have you ever visited a website on internet? There is a good chance that that website was served by using Apache. It is one of the most widely used open source web servers in the world. Wikipedia, that's an easy one, but that's not exactly a software, right? But it follows the same open source spirit. Anyone can contribute, anyone can access the information there. There is no information behind the paywall or secret or anything like that. I throw Python in here because since we are talking about AI here, Python is the programming language that you'll likely use, likely touch one way or another, completely open source. And Firefox. It is an open source web browser that basically letting you to explore the internet. The best part, you can take a look at how these tools are written. You can modify them and even improve them if you want. That's the magic of open source. It belongs to everybody. So, little bit of sum it up for the key principles of open source. It's quite simple. It's free to use, it is modifiable, and it is shareable. And speaking of sharing, you see that little guy hovering down there? That's the Perseverance rover from NASA. And did you know that NASA used Linux and open source software to get to Mars? Like, let me ask you this now. Do you think we would have made it to Mars if the knowledge was locked away? If it was up to just NASA to figure some things out instead of like a people and community already using all those softwares and already improving it? It wouldn't be that soon, I think. But let me tell you why I really, really love open source. And it's not just because it's not just about the free software. It's literally about accessibility, flexibility, and driving innovation, which brings me to the values of open source. As I said, open source is not just about the technology, it's about people working together collaboratively to build something greater than themselves. Like open source is like this movement that powered by collaboration and shared responsibility and like openness. And I believe that this is exactly what you are going to experience during the Hackathon. Like a group of people come together to build and improve and support a project, whether it's an AI related or some other software related, or it doesn't have to be a software related. It could be something creative, different type of project. But it's type of a working environment where there is no boss, like everyone helps in different way to the best of their abilities. Whether it's coding, it's designing, testing, sharing ideas. As the people contribute, the project gets better. And that's why I love open source. Because it's not just about writing the code, it's about building something together, innovating together, and making a real impact. And you might thinking that like that's great, like open source sounds great, but why are you talking about open source? Well, because I love it, as you probably guessed by now, because I truly believe in the power of open source, and because that I happen to work for a company that's actually provides open source products to the companies, to the organizations. So if you go back to the cake analogy, you can think Red Hat as a bakery. Like what we do is that we take the best open source recipes, we experiment, we improve them, we make sure that they work perfectly at scale, and then we deliver a high quality, reliable cake. Sure, you can make your own cake from scratch, right? Because it's free, recipes out there, you share it. But it might take some time, it might require some skills, it might require some tools to get it right. So sometimes it is just faster and easier to go to a bakery that has already perfected the cake. But wait, if the recipe is free, why would anyone pay for it? Like, how does Red Hat make money from open source? Something that we hear quite a lot. Um, you can think of as like you are kind of paying for the future of the cake, because we put a lot of effort into baking new cakes, improving the flavors, like making sure the recipe works for everyone. So when companies using Red Hat services, they are actually supporting the future of open source software. They are actually ensuring that our developers can keep building and securing and innovating. You can also think about that like you're paying for some kind of a professional cooking lessons. Like we don't sell the cake, right? Red Hat doesn't sell the cake. The recipe is always out there, but we help you to bake it better for your own needs, for your own organization, own requirements. So companies usually pay for like support and security and maintenance, some expert trainings so that they can use open source with confidence. So as a company, we work in the open source ecosystem. Whatever we build, they're out there for everybody to see, use, contribute, improve. We all truly believe the power of open source. And we believe that it's essential that we build AI using the open principles, using the same mindset, like with the same community that brought all these like innovative technologies such as like cloud computing, the internet, the Linux, like all these powerful and deeply innovative technologies, we believe that AI follow the same principles. So why I do believe that open source is so important for AI? Um, Truth is, the community or the industry haven't exactly settled on a definition of what open source AI really means. But here is my take on it, right? And why I think applying open source principles are like these values are critical to AI. One is that AI makes everything better. I'm sorry, open makes everything better. Open will make AI better as well. So open researches, open data set means that there's more collaborations, better, there are faster innovations out there. When more people contribute, AI improves as well. And I believe that AI shouldn't be a black box. Like when with open source, like anyone can inspect and audit and improve the models, making them more trustworthy and more reliable. Yesterday there was this talk about ethical AI, brilliant talk. Like if you haven't had the chance to watch it, make sure that you make some time to watch that. So they were mentioning about that, how AI learns from the data, and if the data is biased, then your model will be, biased as well. So if only a few people control the data, then biases can creep in easily. But with open data, where everyone can contribute, where we get more fair and diverse and more representative AI. For example, these like open data, like they're incredibly valuable in the medical field. Especially when it comes to improving the healthcare researches and diagnosis. For example, there is this data set that publicly available. It's called the Cancer Genome Atlas. Like it's sort of a data that like thousands of people diagnosis and patients data, and making that available for researchers, for academics to work on, to build a better, like improving the models out there, it's gonna benefit everybody eventually. And lastly, AI is for everyone, not just for the big tech companies. So right now, building these like powerful AI models like that we interact, like ChatGPT, Gemini, and so on, it requires massive resources, like massive GPU resources, and something only a few big companies have at the moment. And those models, they will always have like an edge in the performance, like they will always perform amazingly. But open source, like bringing open source into AI is more about democratizing this access, like allowing people to run and experiment and like fine-tune models on their own devices without relying on big technologies, big tech companies. There are like open source tools out there, which we will talk a little bit about. And like there are tools like Olama, there are like quantized models, more efficient architectures that help us to bridge the gap, making AI more accessible, even on the lower end hardware like our laptops. So at its core, open source AI isn't just about the code. It's about making AI better and fairer and accessible to all. The more we share, the more we innovate, and that benefits for everybody. That's why I believe that open source is really important for AI. There is just a couple of examples that open source models that you might heard or you can interact with. So these models that for anyone to use, and if you want like improve, whether you want to generate images or like build chatbots or have your own AI assistant, these models can give you freedom of experiment and innovate. Like Stable Diffusion is great for image generations. Bloom is a perfect example of actual collaboration. It's built by over thousands of researchers from all over the world. There's Llama, Granite, Mistral. Those are like powerful language models that can power chatbots. And there is like, for example, Whisper is more speech to text model. So these models are out there, like these models are like out there for us to also like give it a try. So it is not just for these big companies to provide us something. We can also take these things and actually start building some smarter applications or like doing some experiments with them. But AI isn't just about models. It's about like what you do with them. So let's talk about like tools that make them even more powerful. So um, there's this open source AI tools like help us to actually make AI smarter or like help us to collaborate or make them more reliable. Um, Hugging Face, maybe you've heard of it. Is this like open source AI? It's this open source platform that like let anyone to share and collaborate machine learning models. It makes AI more accessible and more community driven. I quite like it. There's Podman AI Lab, for example. It can help you to run the models in a container if you're into containers in your own machine. Anything LLM, completely open source tool that can run an AI chatbot on your local machines. Uh, but I want to bring our focus onto agentic AI framework, and not just because they've been the talk of this year, but also that they are here to address some of the challenges that we have around these large language models. And if you are like me, like to learn how these like challenges turn into innovations, how these how some companies basically address these challenges, and we have now more powerful large language models today, I think you will enjoy this one. So we're gonna talk about agents, and then I will share a couple of open source projects. I will do a little bit of demo, and then we will do a little bit of exercise together. So hope that sounds good to you. Okay, the limitations that I mentioned, for example, up until, to be honest, recently, if you are asking such questions to the chatbots out there, like on the internet, like will it rain tomorrow? it cannot answer to you because, as we said, that those models are bound to data. So they only know the information that from the data that they trained on. So they cannot talk about today or tomorrow. Or maybe they don't have the information, but they might hallucinate and give you some information without any source, like how did they come up with that information, which is not super reliable or not up-to-date information. So agentic AI frameworks, agents come into the picture to address these challenges, and we will gonna see them how it is. So what an agent is, that it is more than a chatbot. It is like this intelligent system that can think, decide, and take action to complete a task. Unlike the regular chatbots that we interact, which what they do is that they predict the next word in the sentence. But an agent can plan its next step, use some tools, and then adapt based on what it learns. So what I mean with that? So let's say that you have this brain with our models, and you are going to tackle these sustainable development goals, right? So let's say that you are gonna focus on the environmental renewable energy side of things, and you wanna know today like how many coal power plants could be replaced with current renewable energy capacity. If you ask this to a chatbot, up until recently, it would answer something like, "Oh, it's hard to just provide you an exact number, but in general, like." Doesn't give you the exact answer that you are looking for. It gives you some ballpark numbers maybe, or some generic informations, because it doesn't have the current renewable energy capacity or how many coal power plants we have today. So how things can be today with these agentic framework developments, think about how you would address these questions. Like, let's say that you are not using any chatbots, but you have an access to internet and you were asked to these questions, or you would like to know the answers for your research. What would you do is if what I would do, I would go to Google and then ask the questions, probably end up with some Wikipedia articles and some articles about the renewable energy, some articles about the coal power plants. And then I will try to extract the information that I need and come up with the answer. That's exactly what we are going to do in here. So you have Wikipedia. You can turn this Wikipedia actually into a tool. So you create a tool out of Wikipedia, basically how you access to Wikipedia. And then you can bind this to the model, which means that now the model knows about that it can talk with Wikipedia if it doesn't have the answer. So if it got the question, the very same question, now that what it can do is that it can formulate a query to Wikipedia. It can formulate something that Wikipedia can understand and then return an answer. So from the question, model can understand that it needs to know current renewable energy capacity. And then it calls the tool, invokes the tool, and then get the answer. So this is the think part of this. Like, it think that it needs to get this answer. It needs to know the current renewable energy capacity, and it acts on it by talking with the Wikipedia and get the response as like the current renewable energy capacity worldwide is approximately something. And then based on that answer, because this wasn't your questions, you want to know how many coal power plants could be replaced with this energy. So it goes back to the tool, ask for the coal power plants, and then get this answer and do some calculation magic and give you the answer. So it thinks, actions, adapts based on what it learned from Wikipedia, and then basically try again until find your answer. Does that make sense? Does that sound powerful to you? And I think I can check the chat again with that. Does that make sense? Awesome. Okay, so what I want us to do now, I want us to see this in a little bit of action with a more like low code, no code type example in the beginning. And I want to really bring you some different open source projects for you to see. So I created this GitHub repository. It's called Teens in AI under my name. And we're gonna, well, first let me get back to here. We are going to use to these four different tools. One is Open Web UI, which is this user-friendly interface to, interact with models, like chat with the models on our own laptop. We're gonna use Ollama, which is an super easy to run. Like it helps us to run the AI models on our laptop very easily. Pydantic is this a framework that helps us to formulate this structured inputs and outputs. So what I mean with that, if you look at in here, I need to send a query to Wikipedia, but I ask, plain English. So Pydantic helps us to formulate this structure and then send the query to Wikipedia or whichever tool that we use. And as the model, as the brain, we will use the Llama 3B model that we can easily download and use. So for this one, what I suggest, just maybe follow me, because depending on your network connection or your computer's speed, like power, it might take some time for you to, download the model and start running that. But what I've done is that in this Git repository, if you go to this weather tool example, this is what we are going to do now. I have step-by-step explanations so that you can do it on your own time, when you have time. Like if you follow this one by one, it's gonna work. And I'm going to now run this one by one to you. The second one, you can do it as well because we're gonna use the Google Colab. So I'm gonna switch a couple of screens now because I need a terminal to download these tools. And then I'm gonna, access to the Open Web UI and start interacting with the model. So the first thing that we'll do is, I hope that this is visible. Oh, sorry, I'm not sure if, why I cannot write in here. Oh, that's interesting. Hold on. Okay, that's the first time that I've seen Zoom just pop up and cancel. Okay, so the first thing that we do is that we create our own Python working environment to make things more clean and more structured. So we have our own Python environment when I will activate it. And the first thing that we do is that we install Open Web UI by using pip install, or there is any other Python package manager you would like to choose. That's also perfect. Things are going to be a bit faster because I downloaded them beforehand, so we don't spend too much time with those things. And then it's like, it looks like a matrix, that's black and green. So Open a web UI, I deploy it, and then I am going to serve it, which means that I am starting this web UI. While this is happening, I am going to open another tab, and I'm going to start the Ollama one, which is going to which is going to serve my model. So I'm gonna again activate the same Python environment. I am going to do pip install Ollama. Done, and then I'm gonna do Ollama serve. Okay, so this is going to serve the model. And now that the Open Web UI is running, it says like go to this endpoint because it is locally. It's not like a web page that have full qualified name. And then the model is in here. I'm just going to go to this one, HTTP 8080. So I'm going back to my browser now. I'm just gonna type it. It's working. It knows that there's a Llama model in the back. And now let's ask that, let's first make sure that it is working. So let's ask, what is the SDG? Maybe let's see if it knows about the sustainable development goals. It knows, and it worked quite fast, actually. That's awesome. Okay, after it knows this, the simplest example to show that like how it doesn't have the current information is you can ask about the weather, basically. Like, what is the weather like today in Istanbul, which is where I'm from? Well, it says, I'm sorry, I'm a language model. I don't have real-time access to the current weather. but it gives me some, still try to be helpful. You can go there, you can look at these things, and you can, get the information. I'm going to rely on the open source community in here. I'm going to rely on the Open Web UI's community. And I know that they are building some tools, just like that Wikipedia in a box. I'm sure that there is something that helped me to fetch the current weather data. So if I go to Open Web UI tools, there is a heap of community that build a lot of tools to help actually to enhance large language model that to overcome this kind of challenges that are like not able to get the current information, not able to access somewhere to do something. So as you see that there are a lot of tools. So what I'm going to do is that I know that I need the weather information. And as you see, there are a number of people who are build some weather tools. So I'm going to pick the first one. And this is written in Python, which means that like it is open, it's out there. You can take it, you can use it. And if there is something that you would like to improve or like some ideas that comes to your mind, you can make that change as well. And the good part is that you can also contribute back. You can find this tool definition like wherever it is in which Git repository, and then you can actually contribute. Like you can tell this person, your weather API is great. Like whatever you build, it's great. I just think that if we change this, the performance will be better, and they will gladly accept it, and you would be, an open source contributor. For now, let's just use it and see how it's gonna be. So I'm gonna copy this code, going back to my Open Web UI. There is this workspace option in here, and there is tools. So there is a small plus button in here. I'm gonna, when I hit it, it's gonna offer me an example, but I want actually whatever I just copied. I want my LLM to access an weather API to get the current weather. So I'm gonna call this weather. And since I like things to be tidy, I'm gonna get this description in here, get the weather tool for a specific city and put it into the tool description. And I hit save and confirm. So now when I try to, when I start a new chatbot, when I hit this plus button, it can see this tool and I'm telling it, enable this tool. I want my large language model to be able to use this in case I ask a question that this tool can help. So I'm gonna ask the same question again. What is the weather like today in Istanbul? Oops, I made a typo, but it's smart enough to probably understand that. As you see that this time it says, according to the provided context, this is the date, this is the time, and this is the information that like it's the 35 Fahrenheit. And you can see that it used the tool. It knows that it doesn't have the answer. It goes to the tool. But the thing is that like Fahrenheit is not the I want to know this in Celsius, like maybe not in Fahrenheit. So I'll get the same question. I'll fix my typo. And I say, can you tell me in Celsius? So, oh, okay. So it said the context does not include information about the Celsius. Would you like to know how to okay, so it's telling me. I was hoping that it would actually do the conversion, but you get the idea. Apparently the endpoint only has the Fahrenheit. And these models that we use, they are not as powerful as like the ones that are out there because we don't have that computing laptop. So you'll see some differences in the answers as well. But I do hope that this kind of gives you the feeling of like what is an agentic system, what is tools, and how large language models use that, and how you can rely on like an open source tools to start experimenting and start building something on your own actually without doing much of coding. Let's see. Okay, the second thing is that this is where I want to introduce similar things, but more powerful. So weather was one thing, but I want to talk about how you can build your own research companion working on your own desktop or some environment like Google Colab where it provides more compute to you, but using with different tool set this time. So we're gonna use Google Colab, and this time instead of like relying on Open Web UI, we're gonna do a little bit of more coding, and we're gonna use a LangGraph, which is a framework that help us to build this type of smart step-by-step like workflows, like applications. And we're gonna create different tools this time, which is like one is DuckDuckGo, like Google search, easy to interact. So we're gonna use an internet search tool. We're gonna use Wikipedia API so that we can fetch some information from there. And then we're gonna use this Python execution environment, because models can do some simple maths, but if you need something more advanced, what you can do is that you can ask the model to actually write the code and then execute the code and only return you to the answer. So this is quite powerful as well. So these Python REPL, these Python execution environment is quite helpful to solve the math problems. And for that, I'm going to go back to the GitHub repository again. I'm going to the first page. And in the second one, there is a link to open the notebook in Opening Colab. So when you click this one, which I'm gonna open in the different tab, it's gonna spin up to an environment if you have the Google account, I believe. And then you'll see that we're gonna use a T4. Oh, okay. So this account doesn't have that. So I'm gonna switch this environment. Sorry, I was gonna do that. So reconnect. So we're gonna use this T4 GPU, which is small enough, it's good enough for what we would like to do. So now I have more powerful environment from what I had before. And again, if you cannot do it right now, this is open, it is there, and I put all the explanations like what each step are doing. And it is at the beginning, it is pretty much the same for what we've done. So what we are going to do is that we are going to install Ollama to run our models, because it's quite easy really using Ollama to serve the model, to start interacting with model. So this shouldn't take so much time. So at the moment it is downloading the Ollama, and then we will start the Ollama, and then we will start binding the tools to our large language models to be able to use those models. And by the way, I learned this trick right before coming to this talk. These cats, I saw it from Robert, who's gonna have the talk right after me. So it's really sweet. Look at these. Like for anybody who curious about this, it is under settings and miscellaneous. There's like corgi mode, there is crab mode. If you wanna change, let's try the crab mode. I think there will be some crabs running. Okay. In the meantime, there is this oh, that's so cute. They're like Ollama deployed. So what we are going to do is we're gonna serve the start Ollama just like we did on the command line, and then we're gonna pull the model. There are different models as well that can run on this T4 GPU, this environment. You can experiment with other models as well if you like. I just try to pick something that is good enough, but not too big to pull down, so we don't spend too much time on these. So at the moment we are pulling down the model, which is like 2 GB or something, shouldn't be too much. Then we will install the libraries we need. We will import these libraries, and then we will do the magic. So, okay, cool. Let's install the libraries. As you see that we are deploying these like LangGraph, LangChain, and then DuckDuckGo search and some Wikipedia libraries, which is just deployed. I'm going down, 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 and I'm importing the libraries. And I am binding the tool. Sorry, I am instantiating the model. And now these are the places where I start defining the tools. But how would I know this? Like where these things are coming from? Again, like LangChain, open source, a good ecosystem. They have a huge tools that has been contributed from people all over the world, companies from all over the world. And I wasn't particularly know how to actually invoke Wikipedia. So what I've done is that I came to this page, I searched for Wikipedia. Luckily it was there. and it is explaining to me what type of libraries I need, what I need to import, and what I need to put in order to actually have a Wikipedia tool. So you can rely on these like open source environments, and then since these are have all like good communities behind, you can also have the conversations. If there is something is not working for you, you can, reach out to them and ask for help, or if there's any improvement you want to bring to the documentation. It doesn't have to be just the code, but documentation is quite important as well. You can do this. So I did same thing for Wikipedia and DuckDuckGo search. I looked at them in the documentation, and this is the definition of the Python REPL execution environment, which is again provided by LangChain. These are like built-in tools. I didn't have to code anything, but I kind of annotated the tool saying that like you are here to do some calculations when needed, if needed, and you need to provide the answer for me. So I am defining this as well. So a list of tools I am given to the model, and this is where I am bind everything together. So this is exactly like what we discussed. So you have this large language model, like you have this agentic system, and you give them some tools. When you ask a question, if the model already knows the answer, it gives you the answer. That's ends. But if it doesn't know the answer, or if it thinks that using a tool is like better to get that answer, it uses the tool, get the answer, and evaluate and think if this is good enough answer, or if it needs to call another tool. So that's why the graph is like this. So either it knows the answer, or use some tools, think about it and act on it, and then make a plan. Should it respond to you or to another tool call? Let's go back to our examples again in the slides, like how many coal power plant could be replaced with current renewable energy capacity. Since these things are a bit deterministic, undeterministic, I do hope that it will give me the answer I saw yesterday. So cool. So what it does is that you see it calls Wikipedia because it doesn't have the answer. So it calls coal power plants that can be replaced with current renewable energy capacity, and then it comes up with some actually Wikipedia results. And then it reads that results, and then it gets back to you. In our case, semi-helpful, but but it does the thinking. So I put a couple of examples to show that how it calls out different tools, or maybe chain the tools, like it gets some answer from DuckDuckGo, then runs some Python execution code. Let's give one or two examples again. So I have another example. What was the first video game console's processing speed, and how does it compare to the current CPU usage of my system? So it needs to know the first video game console processing, which it goes to. It looks at Wikipedia, it looks for DuckDuckGo, but then it also required to run some commands in my own system so that it can figure out my current CPU usage. So it changed some tools. It runs one, get an answer and think about it, then run another tool, get an answer and think about it. And then it kind of gives you that. Basically it gives you that the first one was 1 megahertz, your usage is this and that, and I'm going to give you the answer. So there are a couple of examples that I put here. You can also, if you want that, you can just copy these cells or like create another example, or that you can just change these user query to ask any questions you want. All you need to do is just to go to the collab and then run these cells. Make sure that you have a T4 environment. So this is like one of the ways to show you like quick and dirty how we can do these things. One challenge that I can give you is that there are a number of tools in here. Like there are, for example, a medical publications tool that can go PubMed and search for all these like papers about medical researches, some latest researches. You can try to add another tool to the list by following this documentation, by looking at these codes and then asking some questions around the more medical stuff. So before I finish the hands-on part of this, what I would like to share you, because the reason that I'm giving you a challenge is that in this Git repository, I created these discussions. So one is for the weather example, and the other is for the research companion. So what I want you to do is that join these discussions, share what you've done, share if you did any modification and improvements, and or like if you have any challenge, or like if you blocked in something, just share it. And there will be other people, there will be myself that's gonna help you, just we're gonna have the conversations and we're gonna make things better together. So we're gonna collaborate in open, and that's literally what the open source is about. So make sure that you come here and like test these, go through these examples, and then share your experience, share your improvement ideas. Let me know if you could add another tool to the list, and then, work out with that. So to sum it up, why I am, sorry, excuse me, why all these methods, why I am talking about open source, why I am showing all these open source tools, because it's obvious that AI is shaping the future, but who gets to build that future? Like with open source principles, the answer is all of us. It's you, it's us. It's not just about using AI, but it's about creating and improving and making it accessible to everyone. And as you've seen today, that these like with open source, open weight models and these like tools and approaches like agents, it allows us to experiment, like all of us, build something meaningful, and help us to, open us way to contribute to this movement. And whether you are coding or like you are doing researches or you are just curious about AI, I hope that you walk away knowing that you have the power to be a maker, not just a user in this thing. And it is all this domain is totally open for you to explore. So go out there, just, experiment and build and contribute, and let me know how you do this. All right. So thanks for listening. All right, I'll just stop sharing now.
Hi, Cansu. Thank you so much for your presentation. We have already so many questions from our audiences, so we're happy to. I'm happy to read it out for you to answer. So, one of our audience is asking, is DeepSeek AI by China is an open source code?
So they opened how they how they built the models. That's why I said that like the community or the industry hasn't exactly settled on what is open source, because they settled the approach, they shared the approach, they shared the code, but the data is so massive, data is not out there. So usually you hear that open weight AI concept more than open source, but what they've done is that when they released the paper about how they actually, built that reasoning model, it actually helped a lot of people to, learn the new techniques, learn new features. So in the heart of that, I think it's like the principles are there, but completely open source, that is still like a little bit up in the debate, unfortunately.
Thank you so much for answering. Our audience is asking, where can I get Python?
Oh, I put that link in the GitHub repository. In the first example for the weather tool, the first step is that if you don't have Python, go to this link and download based on whichever operating system that you need, that you are using. So you can find from there.
Thank you so much. How do open source AI projects typically handle data collection, especially in ensuring data quality, diversity, and compliance with privacy regulations?
Yeah, that's a great question. And most of these models are like they share what type of data that they have, but they don't. Not all of them share all the data that they have. So it is quite tricky, because most of these companies buy licensed data in order to train their models, so it is not possible for them to open that. But you kind of have the good faith sometimes that they are using the publicly available data, and then if they are using the licensed data, they are paying for the loyalty, and following the rights regulations to do that. So those things are like still forming, still deciding. United European Union, for example, are looking for this domain a lot at the moment, like building some regulations around that. So it is quite challenging, especially like today, where everybody wants to get into this game and like building the next powerful models, and these regulations are gonna help us to figure these things out.
Thank you. What is CVV and what is open source? Can you clarify that for our audience again, please?
CBB, as in like, hold on, let me check because I have two definitions in mind. As in like, can you clarify what you mean CVV? As in like because there's open source computer vision library that came to my mind, and then there's credit cards. I'm not sure about CV. I'm sorry, I'm not sure about CVV, but well, open source is basically like having these software like out there, like where you can see how it is built, what kind of code that is like entail that. Like let's say that you are using Git, but what you do is that you download the Git as a command line and you start using that. But if you search for it, you can see what actually makes up Git, like what kind of source code behind in order to build that tool. And making it open source is that everyone can use this, everyone can see that. And if you want that, you can also, just take it and modify it for your own needs, or you can improve it and then contribute it back to make it better for everybody. And that's basically open source.
Thank you. We're going to move to the next question. Is Python the only programming language that can be used for open source AI?
Oh no, definitely. Like there is also R, for example, R language that you might hear. It is more on the data analytics side, but my sister, she's a data analyst. She uses R a lot, so I learned a little bit from there. But it is not just Python. But most of the time, you'll see that the data scientist people are using Python to build the models. But the environment changes a lot because now that these models are very accessible, you don't have to build the model, but you build these like surrounding, you start building applications around the models, like these smart AI research companion. And it doesn't have to be Python. You'll see that there is this, for example, agentic system. There is this JavaScript framework that is called B from IBM. So different tools are coming. There is also the Java Marcus, I forgot name, but there's also some Java world is coming to this domain as well. So it is evolving. But usually when you are building an AI model, 99% you'll see Python.
Thank you so much for your answer. Are there any emerging trends in generative AI that we should be paying attention to?
So agents are super hype. That's why I wanted to talk about this. And then there is also this thing called Model Context Protocol. MCP is similar to agents that also enhance the model's capabilities, that help you to actually give more power to do things like access into some, I don't know, like access into some database to insert something, going into some and like going to GitHub to raise some pull requests or things like that on behalf of you. So the other thing that I was thinking about which one I should talk, and agents seems like more popular these days. So there's one agent, and then there's the model context protocol. I would suggest you to look at.
Thank you so much. How can students or young professionals get involved in open source AI projects?
Well, the beauty of open source is that like it is driven by communities, and like there are a lot of communities that get together, whether like it's online or doing some meetups offline. Try to follow those things and try to join them, and that they usually have good some mentorship programs as well, where they're like more experienced and senior people can help can kind of like take you along when they are building something and teach you this base. Check out these like meetups on your city, in your country, if there's anyone that you can join. Super welcoming environment. This is literally the reason that I fell in love with open source when I found out about the concept when I was a student. I started going into the events, and then I started meeting with people, and I learned with them. I grew up with them, and like any project that you are interested in, such as, for example, LangChain, LangGraph, you'll see that there are like discussions happening on the GitHub usually, or in some Slack channels or some Discords. Try to find those things and join that. And I bet you'll find your place and your favorite projects, and some group of people that can help you to get into the project.
Thank you so much. I'm moving to the next question. According to CNN, China's AI DeepSeek claimed to be better than USA's ChatGPT. Do you agree with them?
There are benchmarks there are a lot of different benchmarks out there that doing this kind of a comparison based on the benchmarks. It seems like it is outperforming, but there are like different types of models. Like the DeepSeek's reasoning models is like really impressive. It kind of it explains you the thinking. Like for example, when you are interacting with models online, like you ask a question and then you get an answer. This reasoning model, for example, it explains you how it feels like it gives you the feeling of thinking. Like, oh, the user asked me this, so that like first I need to understand that. It probably asks like this and blah, like try to understand the background. And when you look at this, it's really impressive. Like really give you the feeling that you are actually talking with a person. So according to some benchmarks, yes, like they are good. I enjoy experimenting with DeepSeek as well.
Thank you so much. Moving to the next question. What does the future of open source AI look like in the next 5 years, and how can we ensure it remains sustainable and community driven?
That's a great question. So um, it is obvious that like these open source principles are needed in here, and companies like Red Hat, like us, and some others are really bringing their own experience in the open source for years into this domain. And I believe that the future is really open, and especially these like advancements in terms of the quantized models. Like what I mean is that you know, taking those powerful models and make it able to run on the small hardwares, because the biggest challenge is that at the moment, because the reason that these like big models are kind of driven by the big companies is because they have the resources to that. Like they have the GPU, they have compute resources. But with the advancements on the open source environment at the moment, like anybody become to run and start working with these things. So there will be more and more people actually start getting in. There will be more and more people start to actually contributing, and with that things will start staying more open. People will demand it because otherwise they might not exactly trust it. So the open when I said that open makes everything better is because that you are able to see what about it, like you can audit it, you can build a trust around it when you see that how this thing is getting built, and companies and people are asking for this. So that's why that I definitely believe that the future is open in AI as well. And there will be people like us making sure that this thing is going in the healthy direction. So,
Thank you so much. Another question. What are the biggest challenges in ensuring ethical AI development in open source projects, especially concerning bias and transparency?
yeah, that was it. Like the similar questions were asked yesterday as well in the ethical AI talks, and the most of the concerns are around data, because not all the data are out there. So and basically the models know things based on the data that you provide, and if the data that you provide is like biased or like is not a good representation of every parties, then the model will be biased as well. It's not model's fault. It is us that who is providing the data to make, not ensuring that we have the good representation. So that is literally the biggest challenge when there are like lots of examples out there that how people extract biases from these models by asking some specific questions. There are some papers around that out there you can check. But that's why that there are these checks and benchmarks, like when you would like to use a model because you interact with it, you feel that it is good and you want to bring it into your project, but you would like to make sure that it is not biased. So you can go through these kind of checks and like biases and call these things out, basically, like making sure that we are staying the truth to ourselves and making sure that we are providing the right data and right way of building the model. So that is a challenge. It has still been no, it will keep being discussed, and hopefully when there's more open data, which will bring more fair distribution, things will get better.
Thank you so much. Due to our time limitations, we have to move on with our session. But thank you so much for your insightful talk and your dedication to advancing open source technologies. We're so happy to have you here. Thank you.
That was great. But thanks for all the interactions. Thanks for listening to me, and I'm waiting for your discussions in GitHub. So take care.
Thank you. Thank you, John. Bye.
Thank you. Bye bye.
I hope that Jansu's talk has left you feeling inspired and eager to learn more. And it's now my pleasure to introduce our next speaker, Robert Clarke. Robert is PhD student developing brain-computer interfaces for the control of assistance robots. His focus is on numerographic and biocomputing algorithms. Outside of his he enjoys writing music, traveling, and engaging with the Web3 communities. In this session, Robert will guide us through the fascinating world of biocomputing, discussing how it's developing alongside other forms of computation and what is the future may hold for this rapidly developing field. If you have any questions for Robert, please add them to the Q&A chat and we will address them at the end. Welcome, Robert, and thank you for being part of this event. The floor is yours.
Thank you. Can you hear me? Perfect. Good morning, good evening, good night, wherever you are. I'm really happy to be able to talk to you about this topic. And it's an idea that falls within biocomputing. If you were in my last talk, you would have heard me talk about how we can use living tissue, so brain cells, to be able to do compute. And what I'm going to talk to you today about is how we can do the other side of that. So instead of using the actual neurons themselves, how we can use principles of how neurons function or how brains function to develop algorithms that are similar to the brain or similar to clusters of neurons to do AI-like tasks. All right. So I'm going to share a Google Colab. And what I'll do is then I'll just walk through the Google Colab and all of the different code segments so that you can see how this is actually done and then go through a few examples. Okay, great. So what I'm going to talk to you about today is something called reservoir computing. This goes by a few different names that you might hear. For example, echo state networks. They're a particular type of neural network that are able to do a very efficient compute. So very efficient classification or prediction of a time series, for example, which is really necessary in our world today when we see that our AI systems are using a lot of energy and a lot of data to be able to be trained. What's also really interesting about reservoir computing is that it mimics the structure and function of how we believe the brain to be working very, very loosely, and can be used in a lot of different tasks and can also learn online. So what this means is where with traditional AI algorithms, you need to have a data set and training this data set before you can actually use the algorithm is necessary. With reservoir computing, you can actually take the data as it's coming in, train your network, your reservoir, and then be able to use it instantly. So if I sort of start, what I'm going to go through today is how we can use this type of algorithm for time series prediction. So for example, let's say that we had a weather forecast and you wanted to determine what the weather would be like in the next day or the rain for one day and the amount of rain the next, or even stock prices, taking the previous level, previous price of stock and then determining what it would be the next day. These are the sorts of tasks that are most suitable for reservoir computing, and this just falls under what we call time series prediction. So what's really great about reservoir computing, the reason why a lot of researchers are moving towards this right now, is that it's really simple. You can see in this picture here, we have three parts. We have something called our input layer, we have our reservoir layer, and our output layer. So in a traditional neural network, we have layers, and each of these layers contain neurons that are all connected. But each of these layers have different functions, different what we call activation functions. So think of them as equations that you have to multiply the numbers by. And these things can get very complicated as you train the network to do different tasks and have larger and larger networks necessary to do different tasks as well. But with reservoir computing, what's great is that the input layer going into the reservoir is fixed. So what we mean by that is that all of the connections between the data going in and connecting to the reservoir are static from the beginning. And the same is for the reservoir layer itself. All of the connections in between the neurons of the reservoir are static, they're fixed, and they don't change. How is this different from a traditional neural network? Well, a traditional neural network will have a lot of neurons, but those neurons' connections to each other won't be fixed. This is what we are doing when we're training it. We're training the connections between the neurons. But the reason why reservoir computing works is because what we are using is the natural randomness within the reservoir to take our data and increase its dimensionality. So what that kind of means is we have our data in one form, we pass it through the reservoir, and what we actually are doing is we're reading the state of the reservoir. So what each neuron is doing at every point in time. And this gives us lots and lots of numbers through time that we can then take and put into our output layer. And our output layer is actually another classifier, but a very simple one. So something like a ridge regression, which is you can think of it as a straight line equation. So you can plot a straight line in between these numbers to be able to say this is our classification, or use this to be able to also do time series prediction. So within our reservoir, there are a very few things that we actually need to set. The first one is the input side. So this is how much information you're actually going to put into the reservoir itself. Because what we're going to do is use something like stock market data, our input size is just one. So we're simply going to take one number and pass that into our reservoir. So pretty simple. The second thing that we have to set is the reservoir size itself. So this is actually how many neurons are inside of the reservoir. And this is an important metric because the more neurons you put in our reservoir, the more complex the reservoir is, the more states that to read, and it can then take a little bit longer to train. But at the same time, if we have too few neurons in our network, then it will train very quickly, but there might not be enough information, depending on how much data we're putting in, to then get a very good readout at the end. And then there are two other things that you may not know or may not have heard of that are very specific to reservoir computing. And this is First one is called the spectral radius. Now, the spectral radius, you can think of it as how reactive this system is. So when you put this data in, it's going to kind of make the neurons more active, if you want to think about it that way. And we can set this spectral radius at a number between 0 and pretty much anything. But what we actually find is that a number around 1.
Robert, I'm so sorry to interrupt, but you're frozen right now.
Okay.
Could you please check it with?
Can you hear me?
Yeah, we can hear you, but your screen is frozen.
Okay. Sorry, let me turn off my camera and turn it back on.
Thank you so much. While we are waiting for Robert, please text us from the comment
Is this any better?
section. Yeah, we can hear you, but
Still can't see. Okay.
no, we can't see you.
Okay. If I go out and rejoin this, maybe that might fix it.
Yeah, please do that. Thank you.
Okay.
Yeah, so how are you finding the session? Please text us from the chat while we're waiting for Robert. You guys been so active. We've been looking at the Q&As and the comment section. We're so happy to have you all here. Yes, thank you. Let me read it out for you guys. What's the chat is saying? The session is great, ma'am. It's very interesting. It's lovely learning about new things. Thank you, Cansu. It was such an exciting session. And Robert is back with us. Hi, Robert. So I'm just handing it to you back. Thank
Hi,
you.
can you hear and see me?
Yes, we can hear
Okay.
you and see you. Thank you.
Perfect. Let me know if that happens again. Great. So I'll just pick back up where I left off.
And Robert, I'm so sorry to interrupt you again. Could you please zoom in for our audience for a bit,
Yes,
please?
sure.
Thank you so much. Thank you.
Is that good?
Yeah, perfect. Thank you.
So one of the other parameters that we need to set at the beginning for our reservoir is this idea of the spectral radius. So what the spectral radius is a number that determines how reactive our neurons are to the data that is coming in. We can set this number from anywhere from 0 upwards. But what we find is that numbers around 1 are usually the best. And this actually comes from neuroscience. So this is a quantity that isn't just in artificial neural networks, but we can actually calculate the spectral radius of real biological neurons in neural networks. And we see that natural neural systems have a value of around 1 when we calculate it. And when this number is more towards 0, the neurons are less reactive, they're more stable. And when this number is greater than 1, they are a lot more reactive. So that when the data comes in, it makes their activity a lot more erratic. And then finally, the last parameter is the leak rate. So what a leak rate means is how much the reservoir remembers the information that has just been put in. So for example, if we set the leak rate to 1, then that means that it's only going to be really focusing on the data that's currently put in. But if we lower this number, so we make it smaller than 1, then it takes in account more data that was previously given to it. So the state of the reservoir before is now also taken into account to help it do a prediction into the future. So really, it's a combination of playing with these four parameters and another one, which I'll explain in a moment, that really allows us to be able to do this very, very energy efficient um, classification or time series prediction. And as a comparison, these four parameters plus one more, so it's five, is all that we need to be able to do that versus millions up to billions in neural networks now that we need to train to get similar sorts of classification accuracies. So you can sort of see the order of magnitude in difference in terms of actual computation that needs to be done here. So if we start, first thing we need to do is download these modules, which I've already done. But then the first thing that we're going to actually do is generate some synthetic data. So what sometimes happens is if you try to download data online through Google Colab, there'll be a rate limiting error. So what we're doing here actually is going to simulate some data that will look like stock market data. This is called a random walk. And essentially what we're doing is setting some random numbers, 10,000 different points, to then be able to create our synthetic stock market data. So what we're going to do first is set a random seed. What this will allow us to do is generate the exact same plot every single time. Without this line, the plot that you'll generate every single time will be different. But then we'll just do a cumulative sum of all of the random points for these 10,000 points, and then plot this on our plot here. So here you can see that this now is our time series, and it looks just like some stock market data that you'll see if you were to download it from like Yahoo Finance, for example. And then the next thing that we need to do is normalize our data. So you can see right here, if you look on the y-axis, all of the data is between -20 and well, -40-ish and 100. But what we want to do is make sure the data is all compressed in between 0 and 1. So what this code will do is normalize our data that we've just got here. So it will be exactly the same plot, but you can now see that the data is now a bit more normalized. It's now in the right range to then go into a neural network. And this is just a standard process that we'll do for any type of neural network, because if you don't, then any excessively large or excessively small numbers might skew how the neuron is, how the network is able to learn. So the next part of this is the actual training and building of the reservoir network. So the way that I've set this up is as a class, because there are several different things within this that will need to be made. Sadly, there aren't many packages online that actually allow you to do this in an easy way. So it is more custom-made code that you have to use. But I can see that a lot of researchers are looking into this field right now. So I can see very soon there'll be a lot more off-the-shelf packages available. So if I explain what this class is doing, we make the input size of our network, which I said will be 1. And we also set our reservoir size. So we're just setting the different variables here at the beginning in our initialization of our class. You can ask me some questions at the end about classes if you haven't come across these, but this is essentially just setting all of the different parameters to be then put into our class. And then what we have to do is create something called await matrices for our input and our actual reservoir. So if you're familiar with neural networks, what we're actually doing is we're taking matrices, so think of them as 2D 2D grids to be able to multiply these together. And that allows us to do our calculations just a lot more efficiently. So like I mentioned before, in reservoir computing, we simply have two matrices, one for our input and then one for the reservoir. And that is what is being done here. And then we have another variable here that allows us to scale the reservoir by the spectral radius that we've set here, which is what this function is doing. And then when we are passing our data through the reservoir, we need to be able to update its state. So we need to be able to say, okay, this data has just come in, multiply it by the value that's currently there, remove some numbers because of the leak rate, and then give us a new state. And this is what this function is doing here. And then we need a final function that will essentially run the whole process with all of our input data. Okay. And then what this will do is just run through that whole process for all of the data and then allow us to see all of that in one time series to then plot. So once we have this, I should probably run this. What we want to do is simulate the reservoir. So we want to actually simulate what these neurons in the reservoir are doing and visualize that. So if we take our input size and then we want to set our reservoir size, so how many neurons are in this reservoir, I'm going to just put in a few different numbers so you can see exactly what I mean by the state. If we start with just 3, for example, and then I run this, you can see that we now have 3 lines, and each of these 3 lines is showing the activity of each of the neurons. So this you can think of as like the electrical activity of a neuron. It's kind of the best analogy. It will produce different numbers as data comes in and it's multiplied, as the leak rate is added, as it interacts with the other neurons that are passing data to it. Because remember, each of the neurons within the reservoir are connected to each other. So as all of the data passes around through time, it changes the actual state of each neuron individually. So you can see that as we increase the number of neurons, so if I make this 30, for example, things start to get a lot more complex. And it's this complexity that allows us to be able to do time series prediction. Because once we take this data and put it into our readout layer, it's actually a lot more what we call sparse. And it allows the readout layer to be able to basically draw a line of best fit through it. I know it doesn't look that way from this plot, but that's because I'm plotting all of the data through time all at once. But then this is where we do the final training. And this is the only thing within a reservoir computing framework that we actually need to train. The final linear regression model that this data is going into. So we take a ridge regression model, which is, like I said, like a line of best fit, if you think about it like that. And we can set our model with a regularization parameter. So it kind of makes sure that it doesn't overfit. And then we can take the states of the reservoir versus what it should be and fit our line to that and make our predictions. And then this line does our plotting. And then we finally do a calculation to compare our prediction with the actual value that it should be. And what we're using for that is the mean squared error. So the mean squared error basically is one of many different types of metric that we can use to evaluate how good the performance of our network is. So if I run this, what you can see is that this network has performed very, very well, because the actual is in blue and the red is in predicted, and the is our predicted, so what the reservoir has actually come out with. And you can see that it pretty much perfectly overlaps this this the actual plot. There are only a very few points where it doesn't, but that's actually the power of reservoir computing. It's perfect for time series prediction. It's able to do this with very, very little compute resources. I mean, we were able to do this on Google Colab without having to use a GPU at all. And if you were to use something like a deep neural network, you definitely need to use a GPU. If we look at the mean squared error, we have a value of 0.001, and that is quite good, because the closer to zero you are, the better it is. So that is pretty much reservoir computing. And like I said, it is a very simple and straightforward algorithm to use. You set up the reservoir, you pass the data in, you simulate, and then you compare the prediction versus the actual. But what I want to do here is just show you actually how the different parameters impact the performance of your algorithm. So here we have a few different things that we can change. Like I said, Like I said, we want to be able to change the number of neurons. So that's what this first one is. We want to be able to change the spectral radius, the leak rate, and we're also able to change this, the regularization of that readout layer. So the only thing that we're training, there's one parameter within that we can also train. And this other dial is just making the data a little bit harder to model. So you can see here we kind of add noise to the data to make it a little bit more jagged. So if I choose a alpha, so a regularization in the readout layer that's too high, you can see that our line is now not following the real data at all. So this is why training that readout layer is really, really important, because then it really doesn't matter how big your reservoir is, how you really change the spectral radius or the leak rate. It doesn't really have a good accuracy. I mean, this is not that bad, but you can see here at the very end, it's really not being able to capture this pattern here or any of these peaks. So if we bring down this alpha into a range that's better, then we see that the prediction actually starts to get better as well. And if we bring down the number of neurons and we bring up the spectral radius, you can start to see actually how each of these different parameters impacts the performance. So it's very, very, one of the things that you have to do is pick which ones of these you want to stick with. So let's say we're going to stick with a reservoir that has 100 neurons. What you have to then do is probably do something called a parameter search around these other parameters to be able to know which one is the best. Like I said, the spectral radius around 1 is usually ideal. So this is kind of given. You don't have to do too much searching around parameters for that. But things like the leak rate and then also the alpha for your readout layer, these are things that you're going to want to play around with a little bit to be able to get the right sort of values to get a good classification. And you can see here that having the alpha as low as possible is actually the best thing for this particular network, because as you increase that, it doesn't perform very well. Right. So that is my little workshop on reservoir computing. I know it was kind of a lot to go through in a short period of time, but this is what I think is going to be one of the most used algorithms in the next years for time series prediction, purely because it has a lot of applications. It can be used in a lot of applications that allow for compute to be moved away from large data centers and onto what we call edge devices. So, for example, this sort of algorithm would be possible to run on your phone. You could run it on any kind of hardware that doesn't have a large GPU, and that will bring AI or this kind of predictive computing a lot closer to where the data is. And I mean, that's good for energy consumption, good for data consumption as well. Right. Thank you.
Thank you so much, Robert, for your presentation. Now we're moving forward with our Q&As from our audiences, and they're really inspired by your presentation, so that we have quite a few. So one of the questions is, what is exactly reservoir? I think
Reservoir.
Yeah, reservoir. Yeah.
So the reservoir is a collection of neurons, and they're all connected to each other. So an interesting analogy is the brain. The brain can be considered as a reservoir. We have lots of neurons all around, and they're all connected to each other. I mean, they're not all connected to each other, but there is a structure, and that structure is fixed. And that's the main thing to think about here. If you think drawing a lot of dots and then just drawing lines in between all of them to connect them together. This is what a reservoir is.
Thank you so much for your answer. We are moving to the next question. Where we can train to do such experiments?
Yeah, so like I mentioned, there's sadly not that many different Python packages that you can just download and use. But I can share this script and you can play around with it. I mean, in general, there's ChatGPT. There's a lot of different chatbots that you can use to help you develop these sorts of things. And then, like I did here with Google Colab, you can simulate data. You can get data from other places to be able to do pretty much anything. So classification and time series prediction are the best things to use reservoir computing for.
Thank you so much. Another question is, what are the noise level and ridge alpha variables are for?
Yeah, so in my example, the noise level was just so the data that it was trying to model would be a little bit harder to model. So because it's not real world data, I just wanted to add a little bit of noise. So this is a concept in computer science. Adding noise just means adding a little bit of randomness to your data. And the ridge alpha, so I remember saying there's three parts to your reservoir computing framework: the input, the reservoir itself, and then the readout layer or the output layer. The output layer is a classifier in itself, and it has a parameter that needs to be tuned to allow it to interpret the reservoir states. Sorry, give me a second. Light. Yes. So the ridge alpha has a parameter itself that needs to be tuned to be able to interpret the state of the reservoir, and that's what that is.
Thank you so much. Another question is, what made you interested in AI in the first place?
Yeah, so what interested me in AI, it's actually quite interesting in itself. So I was originally doing my undergraduate in biomedical science, and I was doing a project in drug discovery, so uh, developing chemicals that could interact with neurons. And I started to look into how that software actually works, and I was reading about this idea of training sets and test sets, and I found that just really interesting that how you could use data and learn from it to then do biology. And looking into that further, I just thought, yeah, this is something I want to do after learning that AI is really just maths. So I think that's kind of what really drove me towards it.
Thank you so much. Moving on to the next question. If each neuron is connected and data passes through, does it also change the positions of the neuron?
No, no. So everything about the reservoir and the input is completely fixed. The neurons are static, and the only thing that changes about the neurons is their state. So you can think about that as what number uh, it contains.
Perfect. Thank you. What other resources do you suggest to explore further to understand the basics of this emerging technology? Any other learning courses you suggest?
Yeah. Um, so reservoir computing itself is quite new in terms of its use. It's not new in terms of the ideas, but they've been largely just confined to academic research. Sadly, there aren't any courses that I've seen that incorporate it. Um, I think I think if you're interested in this as a concept, um, just looking at what's available online, looking at other things like liquid state networks and echo state networks would be good. Um, but like I say, a lot of it is academic papers. So what I always do recommend is taking these papers and putting them through a language model and getting them to summarize and simplify and explain how what they're doing functions. But the beauty of reservoir computing is that it's there isn't a lot to do. It's set these parameters and then pass data through it. Um, the only kind of hard part would be the optimization of the parameters, so choosing what numbers to actually set those at. So I wouldn't even say that doing that would be hard.
Thank you so much. Since biocomputing is still new, what are the ways to create awareness about it, as not a lot of people know about biocomputing?
Sorry, you cut out on my end. Could you repeat that question?
Of course. So, since biocomputing is still new, what are the ways to create awareness about it? Not a lot of people know about biocomputing.
Yeah. Um, I mean, the best way is really things like this. So talks, um, and really just talking about it. I don't really know if there's any other way right now because it's quite early, so there isn't much to show in terms of real world use cases just yet. Um, I can see that there will be some real world use cases definitely in the next few years, but they won't be super functional if that makes sense. So, for example, I previously showed that a group was able to play Pong with these neurons, but playing Pong isn't necessarily something that is going to be super useful for everyone and make it something that everyone talks about. It's just sort of something that's quite cool. Um, so we'll definitely see a lot of that in the near future, which will get people talking, and I think that's probably where it's going to be for the time being.
Thank you so much. How do you ensure the security and privacy of neutral data in BCI systems?
Okay. So that's actually a really interesting question. Um, because right now there's a lot of talk about, okay, should we integrate blockchain systems? Because blockchain is inherently cryptographic. So you put the data and you hash it, so you convert it into a string of numbers that you can't read. So this is one way of making sure that neural data can be secure. And other ways are things like federated learning. So because BCI systems have to have an algorithm attached to them to decode the brain signal, instead of taking that brain signal and then putting it into the cloud, you can actually do all of the compute locally, so right next to the person on a device, and all of the learning is done there. So no data actually moves from the BCI to any other place. The learning happens where the data is collected, and then if there's a model that needs to be trained and improved, the parameters from the local model get put into the cloud, so no data is actually transferred.
Thank you so much for your answer. We're moving to our next question. What are the different data types that will be used in creating a chatbot and how it can be used?
So it's interesting because with chatbots, if you think about them as what they're made up of, rather than okay, these are things that I can talk to. So they're made of transformers. Um, they can take in a lot of different types of data. It doesn't have to be text. I've seen ChatGPT like algorithms be used with biological data. So if you think of that, you can pretty much turn any data into a string. Um, so mostly you're looking at text, so letters and numbers. But if you can turn your data into letters and numbers, that's in a unique way, then it can pretty much be anything. So for example, you can represent chemicals as what are called smiles strings, so just letters. And you can then put that into a chatbot-like device to be able to do generation.
Thank you so much for your answer. How could biocomputing play a role in making BCIs more accessible and affordable?
Yes. So that's actually what I work on. I work on using neuromorphic algorithms, so algorithms that like reservoir computing and echo state networks to make sure that the compute is a lot more efficient and it can be on device. Um, Making them more accessible and affordable isn't just down to the algorithms though, because there's hardware. You have to be able to get the signal from a person's brain to be able to classify it, to be able to get it to do something. So there's a little bit more than just the algorithms themselves. But if you are using algorithms that don't require um, very energy intensive hardware, then that's one step in the right direction.
Thank you so much. Which package can be used for this real world data is one
Um,
of the questions.
yeah, so if you want to um, do work like this, but then to incorporate real world data, then you can use Yahoo Finance. That's one. You can then take actual stock market data to be able to feed that in as a time series. Another one that's quite good is Google Trends. So you can get the the historical usage of any word or phrase from Google as a time series to be able to do a similar sort of time series prediction. Um, there are a few others. Let me think. So those two are good because they are just downloadable through a pip install, so you can just write some code and then use them right away. There are a few others that, so I think the Federal Reserve has, like the American Federal Reserve has a package itself that allows you to download data, but you need an API key, which you probably can get. And yeah, those are probably the good examples to start with.
Thank you so much. What breakthrough What breakthroughs are needed for neurographic computing to become mainstream, and how do you see its roles evolving in AI over the next decade?
Yeah, so I mean, we're seeing quite a few breakthroughs in neuromorphic computing right now. The the I think what what we're missing are more accurate models of neurons. I think that is one of the major um, bottlenecks that we have right now because we understand where these are useful, but being able to simulate a neuron digitally accurately, we're still not entirely there yet. We have a lot of different ways of doing that, but that's the problem. We have lots of different ways of simulating neurons. So which one is the best? And then also converting data into a data type that is compatible with different neuromorphic algorithms. So this one that I showed you is perfect for using data as it is. We can just put the data in as numbers. However, there are other types of algorithms that, for example, spiking neural networks that work by mimicking the actual functioning of a neuron. So you have actual spikes in the same way neurons have spikes, meaning that the data needs to be converted into spikes. So doing that in an efficient way for all data types is also a a bottleneck.
Thank you so much. Can you share some insights on the use cases for leveraging and integrating quantum computing for biocomputing?
Yeah, so quantum computing and biocomputing can come together in the sense of using reservoirs. So if you were to take a neural organoid, so a three-dimensional culture of neurons, this could be considered a reservoir. So you can do the exact same sort of things that I was talking about here by reading the states of the organoid, so the spikes. And also you can do a very similar thing with a quantum reservoir. So reading the state of the quantum reservoir and the neural reservoir themselves, these two things can in some way be combined. So what I've seen being done in literature, not with quantum and neural reservoirs, but with just um, reservoirs themselves, is by connecting them. So you pass data through one, take the data out of one and pass it through the other, and that actually increases the classification accuracy overall, because what you're doing is you're putting data in, making it more readable, and then you're putting that data into another reservoir and making it even more readable. So if you were to do that with a quantum reservoir and then a neural reservoir, or maybe the other way around, then you get the same sort of effect.
Thank you so much. Moving to our next question. How does biocomputing help tackle STEM problems?
STEM problems. So I'm assuming STEM as in science, technology,
Yeah.
So, I mean, what's really interesting about biocomputing is that it combines two fields. It combines biology, it combines computer science. I mean, there's a lot of math in that as well because you need to understand how a neuron or any kind of biological system functions, but then be able to put that in a mathematical way. So I think because of the cool factor of it as well, it can really draw people into wanting to maybe learn the math behind it and wanting to and seeing that okay, there's a little bit more to computer science because I can do biology with it, and there's a little bit more to biology because I can actually do computing with it too.
Thank you so much. Due to our time limitations, I'm just going to ask you one more question from our audiences. Numero Nomographic chips are often inspired by the human brain. How close are we to replicating true brain like computation, and what are the biggest challenges?
Yeah, so in terms of how close are we to replicating the human brain? We're not very close to replicating the human brain because it's so large and um, we, for example, we've only managed to really image and replicate a small section of the mouse brain. There's a lot of initiatives looking to to do exactly this, though. Whole brain emulation is a field of itself. Um, and what they tend to do in this field is take electron microscopy slices of neural tissue and then model this and try and build a bigger picture from these smaller starting points. Other people have tried to replicate the brain computationally. So rather than going from the individual neurons, try to computationally model different functions. And even with that, again, we haven't managed to do every function of the brain. There are some groups that have managed to do modeling the speech. So how the speech part of the brain then allows our tongue and mouth to move and produce sound. There are other groups that have modeled how the motor cortex is able to produce muscle movements, individual muscle movements in the hand, but not the full body. So there are kind of two different ways of looking at it, but we're still very, very far away from replicating the whole brain. Um, yeah.
Thank you so much. Even though we have time limitations, our audiences are actually so inspired and asking so many questions. So I'm just gonna have one more question for you.
Okay.
What are some leading companies in the biocomputing in neuromorphic chips?
Yeah. So in terms of biocomputing, you have Cortical Labs, you have um, Final Spark. These are two of the biggest ones. In terms of neuromorphic chips, there's a company called Rain AI, and they're probably the biggest one. But also Intel. Intel has a lot of research into making neuromorphic chips as well, and I'm sure there will be a lot more popping up. There's a lot of this is still in academic research. Um, there aren't that many neuromorphic chips on the market, but they're very close to being on the market.
I've checked it with my team, and we see that our participants are really engaging. So we're gonna still continue with our Q&A.
Okay.
Can nomographic computing aid the formation of cells?
No. So stem cells and neuromorphic computing are a little bit too far apart to be able to really help each other, at least physically. I mean, AI seems to be quite useful in all areas. Potentially, you can use a neuromorphic chip or a neuromorphic algorithm to help design a protocol to then help how you design your stem cells or grow your stem cells. Um, but nothing direct that I can see right now.
Thank you so much. Another question is, how about Elon Musk's Neuralink? It's different by
So Neuralink, what they do is they have created a brain-computer interface that's implanted into the brain, and it's implanted using wires. So the way that their system is different from the stuff that I do, for example, is that it's what we call invasive. So you have to have a surgery, and well, they don't actually do a surgery, they use a robot to implant it into the person's brain and then inject those wires into the brain to be able to connect to it. The thing that's different about that is from what I do is that I don't have any wires implanted in anyone's brain. They put on a EEG cap and it measures the signal from outside of the brain. There are lots of other companies like Neuralink that have developed invasive brain-computer interfaces. For example, BlackRock Neurotech, they have a system that has electrodes that go into the brain, but that causes damage to it more than what the Neuralink device does. And then you've got others like Synchron that have devices that go into the blood vessels, and then they sort of incorporate into the blood vessel and record from there. So there's kind of a whole array of different devices that you can use to record from the brain.
Thank you so much. How can students and researchers get involved in biocomputing in neuromorphic AI development?
Yeah, so with neuromorphic AI development, there are a lot of open source packages. So I did mention that reservoir computing, there don't seem to be that many. But with just simulating neurons, so for example, there's Pine, Pynn. That's a Python-based package that allows you to simulate neurons, and that could be one way of getting into this, because if you know Python, then you can get started with this quite easily. There's another called um, SNN Torch, or Spiking Neural Network Torch. If you've heard of PyTorch for training neural networks, then this is another that you can use. And this is for training spiking neural networks. These are networks that work similarly to a um, biological neuron, but like I said, we still don't fully understand how a biological neuron works to be able to efficiently model them. And then there's another called Brian 2. So Brian 2 is another one of these simulators to be able to start to work on how we can build a virtual biological neural networks.
Thank you so much, Robert, for your presentation and answering our participants' questions. We're so happy to have you. Thank you so much.
Thank you.
Thank you so much, everyone, for joining us today. We had exciting talks coming up through the week, so stay tuned for tomorrow's session. If you missed any sessions throughout this week, in the chat, we have the link, so you can definitely go and check and get more insights on other speakers that you've missed, because they were here for you, and we're so happy to have you all here today with us. And I would like to thank our sponsors, Sage Foundation and Red Hat, for their contributions to this session. So thank you all for joining, and see you tomorrow. Bye, everyone.